In the vast and silent reaches of space, stars are born, live out their radiant lives, and eventually die, leaving behind the seeds of new worlds and future suns. Their story is not simply one of light and heat. It is the grand cycle of creation and destruction that shapes the entire universe. Every atom of carbon, iron, and oxygen in the human body once belonged to a star that lived and died billions of years ago. The birth and death of stars are not just cosmic events, they are the very reason life exists at all. It all begins within enormous clouds of gas and dust known as nebulae. These immense, cold regions, often stretching for hundreds of light years, are filled primarily with hydrogen, the simplest and most abundant element in the cosmos. Over time, gravity begins its quiet work. Slight variations in density cause portions of these clouds to clump together, attracting more and more material. As the cloud collapses under its own weight, it begins to spin faster, forming a dense core surrounded by a swirling disk of gas and dust. This dense, contracting heart is called a protostar, the first stage in a star's life. As gravity squeezes the protostar tighter, its internal temperature rises. At first, the light it emits is only from heat generated by compression, glowing dimly in infrared wavelengths. But as millions of years pass, pressure and temperature at the core increase until hydrogen atoms begin to fuse into helium. This moment, the ignition of nuclear fusion, is when a true star is born. The balance between the inward pull of gravity and the outward push of energy from fusion creates a stable equilibrium. The newborn star begins its long life on what astronomers call the main sequence. Most of a star's existence unfolds quietly in this phase. Here, fusion steadily converts hydrogen into helium, releasing enormous amounts of energy that shine across the universe. Our Sun, about 4.5 billion years old, is a main sequence star. It has enough hydrogen fuel to keep shining for roughly another 5 billion years. Larger stars, however, burn through their fuel at a much faster rate. A star 10 times more massive than the Sun may live for only a few million years, while smaller stars, known as red dwarfs, can endure for hundreds of billions of years, far longer than the universe has currently existed. Inside a star, the processes are astonishingly complex. Temperatures in the core can reach tens of millions of degrees, allowing nuclear fusion to occur. In the Sun's case, every second, about 600 million tons of hydrogen are converted into helium, releasing energy equivalent to billions of hydrogen bombs detonating at once. Yet the balance is so perfect that this energy spreads smoothly through layers of plasma before escaping as light and heat. As a star exhausts its hydrogen fuel, equilibrium begins to fail. The core, now filled with helium, cannot sustain the same fusion reactions as before. Gravity starts to win, causing the core to contract while the outer layers expand dramatically. The star swells into a red giant, growing hundreds of times its original size. When our Sun reaches this stage, it will expand far enough to engulf Mercury and Venus and perhaps graze Earth's orbit, turning the sky into a blazing red ocean of fire. For more massive stars, the story grows even more violent. As they fuse heavier elements, carbon, oxygen, neon, silicon, the process becomes increasingly unstable. Each fusion stage produces less energy until the core finally builds up iron, an element that cannot release energy through fusion. In that instant, the delicate forces collapse. The star's core implodes under its own immense gravity, triggering one of the most powerful events in the universe, a supernova explosion. In a fraction of a second, the core collapses to an ultra-dense sphere of neutrons, while the outer layers are blasted into space with such force that they outshine entire galaxies for a brief moment. The shockwaves scatter the elements forged in the star's heart, gold, silver, carbon, oxygen, and many others, across interstellar space. These materials eventually blend into new nebulae, forming the building blocks for future stars, planets, and even life itself. If the remaining core is small enough, it stabilizes as a neutron star, a city-sized object so dense that a teaspoon of its matter would weigh billions of tons. But if the core's mass exceeds roughly 3 times that of the Sun, not even neutrons can withstand the gravitational pressure. The collapse continues endlessly inward, creating a black hole, a point in space where gravity is so extreme that not even light can escape. Black holes mark the ultimate fate of the most massive stars, silent witnesses to the universe's most cataclysmic births and deaths. Smaller stars end their lives more peacefully. When a sun-like star exhausts its fuel, it sheds its outer layers into space, forming a glowing shell of gas called a planetary nebula. At the center remains a white dwarf, an object roughly the size of Earth but containing half the sun's mass. Though no longer generating energy through fusion, it still glows with the residual heat of its long life, slowly cooling over billions of years until it becomes a cold, dark remnant known as a black dwarf. None of these black dwarfs exist yet, as the universe is not old enough for even the oldest white dwarfs to have fully cooled. The birth and death of stars are the cosmic heartbeat of creation. Each generation of stars enriches the galaxy with heavier elements, building a more complex and vibrant universe. The oxygen you breathe, the calcium in your bones, and the iron in your blood once were formed inside the fiery core of a star that lived and died long before the Earth existed. In a very real sense, we are the universe made conscious. Born from the ashes of ancient stars, destined to gaze back into the night sky and wonder at our origins. From the quiet collapse of a cold nebula to the roaring death of a supernova, the life cycle of stars is the most profound narrative ever written across the heavens. A story of fire and dust, of endings that become beginnings, and of light that continues to travel long after the star that created it is gone.
The secrets of exoplanets. Across the vastness of the Milky Way, far beyond the familiar glow of our Sun, countless other stars host their own worlds, some rocky, some gaseous, and some so strange that they defy imagination. These are the exoplanets, planets that orbit stars outside our solar system. For most of human history, their existence was only speculation, the stuff of dreams and science fiction. Yet in the past few decades, that dream has transformed into a scientific revolution. Astronomers have discovered thousands of these distant worlds, revealing that planets are not rare at all, but a natural and abundant outcome of star formation. The discovery of exoplanets has forever changed our view of the universe and of ourselves. The search for other worlds began not with giant telescopes or space probes, but with a question as old as civilization itself. Are we alone? For centuries, humanity looked up at the night sky and wondered if those distant points of light might harbor other Earths. But it was not until the final years of the 20th century that technology advanced enough to detect the subtle clues of planets orbiting other stars. In 1995, astronomers Michel Mayor and Didier Queloz announced the first confirmed detection of an exoplanet, a world known as 51 Pegasi b. This massive Jupiter-like planet orbits its star so closely that a year there lasts only about 4 Earth days. It was an extraordinary discovery, a gas giant circling closer to its star than Mercury does to the Sun. The findings shattered long-held theories of how planetary systems form and forced astronomers to rethink everything they thought they knew. Since then, the discoveries have come in waves. Using instruments like the Kepler Space Telescope, scientists have detected thousands of exoplanets by observing the tiny dips in a star's brightness as a planet crosses or transits in front of it. This method, known as the transit technique, allows astronomers not only to find planets, but also to estimate their size, orbital period, and even hints of their atmospheric composition. Another powerful method, called the radial velocity technique, measures the slight wobble of a star caused by the gravitational tug of an orbiting planet. By combining these two approaches, astronomers can determine a planet's mass, density, and sometimes even its weather patterns and chemical makeup. What they have found is astonishing. There are hot Jupiters, gas giants orbiting so close to their stars that their atmospheres boil away into space. There are super-Earths, rocky worlds larger than our planet but smaller than Neptune, with crushing gravities and thick atmospheres. Some exoplanets orbit two stars at once, like the fictional Tatooine from Star Wars, bathing in twin sunsets. Others are rogue worlds, drifting alone in the cold darkness between stars after being flung from their birth systems. The diversity of these worlds reveals that the universe is far more creative than we ever imagined. Some exoplanets rain molten iron or glass. Others are believed to be covered in global oceans tens of miles deep. On one known as WASP-12b, the intense heat from its nearby star stretches it into an egg shape and slowly consumes its outer layers. Another, called Kepler-16b, orbits in perfect harmony around a binary star system, a real-world example of a double sun sky. These discoveries show that the architecture of planetary systems is wildly different from our own. The familiar layout of small rocky worlds near the sun and giant gas planets farther out may be only one of many cosmic patterns. Among all these alien worlds, scientists pay special attention to those that orbit within what is called the habitable zone, the region around a star where conditions could allow liquid water to exist. Water is essential for life as we know it, and the presence of a stable, temperate environment is one of the key requirements for biological processes to emerge. Many Earth-sized planets have now been found in this Goldilocks zone, where it is neither too hot nor too cold. Some of these, such as those in the TRAPPIST-1 system, orbit a small red dwarf star only 40 light-years away and could have oceans, rocky surfaces, and atmospheres capable of supporting life. But habitability is far more complex than distance alone. A planet's atmosphere, magnetic field, and geological activity all play critical roles. Without a protective atmosphere, a planet would lose its water to space, as happened to Mars. Without volcanic recycling of gases, the atmosphere could stagnate, trapping heat or freezing out essential elements. Astronomers now use sophisticated models to study how these factors interact, combining data from telescopes like the James Webb Space Telescope, which can analyze starlight filtered through a planet's atmosphere during a transit. Through this technique, scientists can detect the chemical fingerprints of water vapor, methane, oxygen, and even carbon dioxide, molecules that might hint at biological activity. Each new discovery brings us closer to answering one of humanity's oldest questions: are we alone in the universe? If there are billions of stars in our galaxy, and most have planets, then the number of potentially habitable worlds could easily reach into the tens of billions. Somewhere among them, life might have taken root. Maybe microbial, maybe intelligent, maybe unimaginably different from anything on Earth. The implications are profound. Finding evidence of life elsewhere would not only transform science, but also reshape philosophy, religion, and our sense of identity as a species. Exoplanet research also deepens our understanding of how planets form and evolve. Observations show that planetary systems emerge naturally from the same disks of gas and dust that give birth to stars. Within these rotating disks, dust grains stick together, forming clumps that grow into planetesimals and eventually full-fledged planets. The composition and temperature of the disk determine what kind of planets form where. In the inner regions, where it is hotter, rocky planets dominate. Farther out, where it is colder, ices and gases accumulate into giants like Jupiter and Saturn. These patterns help explain not just distant systems, but also the origins of our own solar neighborhood. Today, the search for exoplanets continues with breathtaking speed. The James Webb Space Telescope, launched in the early 21st century, is already studying the atmospheres of distant worlds with precision that was once unimaginable. Future missions, such as the Habitable Worlds Observatory, will go even further, capable of directly imaging Earth-like planets and searching for the faint glow of biosignatures. These missions will not simply look for planets that resemble Earth, but for worlds that expand our definition of what life might be and where it could thrive. The secrets of exoplanets remind us that the cosmos is both familiar and alien, governed by the same physical laws, yet filled with endless variations. Every discovery is a reminder that our solar system is not unique. It is one of countless others in a galaxy teeming with worlds. The night sky, once seen as a silent backdrop, is now understood as a living panorama of suns and planets, each with its own story to tell. And somewhere among them, perhaps on a blue world circling a distant star, another being may be looking up at their own night sky, wondering if they too are alone.
At the outer edge of human understanding, where space and time twist into something almost unrecognizable, lie the most mysterious and terrifying objects in the universe: black holes. They are regions where gravity has grown so intense that nothing, not even light, can escape. To stand near one would be to gaze upon the ultimate power of nature, a point where the known laws of physics break down. And yet, black holes are not just destroyers. They are engines of galaxies, forges of energy, and silent archivists of cosmic history. The story of black holes is a journey into the very fabric of reality itself. The idea of a body so dense that even light could not escape dates back centuries. In the late 18th century, British natural philosopher John Michel and French mathematician Pierre-Simon Laplace both speculated that such dark stars might exist if a body were compact enough to exert an escape velocity greater than the speed of light. But it was not until Albert Einstein's general theory of relativity, published in 1915, that the concept became more than speculation. Einstein described gravity not as a force pulling between objects, but as a curvature of space and time caused by mass. In this new vision, a black hole is not an ordinary object. It is a region where space itself has collapsed inward, forming a well so deep that escape is impossible. Only months after Einstein published his theory, the German physicist Karl Schwarzschild found an exact mathematical solution that described such an object. This became known as the Schwarzschild radius, the critical boundary beyond which gravity becomes infinite. That boundary, now called the event horizon, marks the point of no return. Anything that crosses it, whether matter, light, or radiation, is forever trapped. Inside, all paths lead inward toward a single point of infinite density and zero volume, the singularity. At the singularity, the known laws of physics no longer apply. For decades, black holes were dismissed as mathematical curiosities, too bizarre to exist in nature. But evidence slowly began to build. Astronomers observed stars in binary systems that appeared to orbit invisible companions far more massive than themselves. The only explanation was a collapsed star, what we now know as a stellar mass black hole. Such black holes are born from the death of massive stars, those more than roughly 3 times the mass of our Sun. When these giants exhaust their nuclear fuel, gravity overwhelms the remaining pressure, and the star's core collapses catastrophically. The outer layers are blasted away in a supernova explosion, leaving behind an object so dense that not even light can escape its grip. As decades passed, astronomers discovered black holes not only in stellar form, but on a staggering scale at the centers of galaxies. These are supermassive black holes, containing millions or even billions times the mass of the Sun. Our own Milky Way harbors one, known as Sagittarius A star, located about 26,000 light-years away. Although it is invisible, its presence is revealed by the furious dance of nearby stars whipping around an unseen point at incredible speeds.
The first direct image of a black hole came in 2019, when the Event Horizon Telescope captured the shadow of the supermassive black hole in the galaxy M87, a glowing ring of plasma encircling darkness itself. That image, humankind's first look at the unseeable, confirmed a century of theory. Black holes come in several varieties, determined by how they form and how massive they are. Stellar mass black holes are the remnants of dying stars. Supermassive black holes lie at the cores of galaxies, shaping their evolution and influencing star formation across millions of light years. There may also be intermediate black holes, those that bridge the gap between stellar and supermassive scales, though their existence remains difficult to prove. And some theories suggest that primordial black holes, formed in the chaos of the early universe, could still be lurking unseen, no larger than an atom, but with masses greater than a mountain. The environment around a black hole is one of the most extreme in existence. As matter spirals inward, it forms an accretion disk, a swirling maelstrom of gas and dust heated to millions of degrees by friction and gravitational compression. The energy released in this process can outshine entire galaxies. Jets of charged particles traveling near the speed of light are often ejected from the poles, extending for thousands of light years. These jets, though launched from the edge of darkness, may actually seed the surrounding cosmos with elements and energy, helping to form new stars and planets. In this paradoxical way, black holes act not only as destroyers, but also as creators. Time behaves strangely near a black hole. According to Einstein's theory, gravity warps not just space, but time itself. The stronger the gravity, the slower time flows. For an observer approaching the event horizon, time would appear to stretch infinitely, while to a distant observer, the infalling traveler would seem to freeze at the edge, fading gradually from view. Yet from the traveler's own perspective, they would continue inward, crossing the event horizon and plunging toward the singularity in a matter of seconds. This distortion of time and space is not just theoretical. It has been confirmed through precise astronomical measurements and forms the foundation for our understanding of how black holes interact with the rest of the cosmos. One of the most profound insights came from the physicist Stephen Hawking in the 1970s. Using quantum theory, Hawking demonstrated that black holes are not entirely black. Tiny fluctuations in the fabric of space-time allow pairs of particles and antiparticles to appear and annihilate near the event horizon. If one particle falls into the black hole while the other escapes, the black hole loses a tiny amount of mass. Over immense timescales, this process, known as Hawking radiation, could cause black holes to slowly evaporate and eventually vanish. This discovery connected the realms of quantum mechanics, relativity, and thermodynamics, three pillars of modern physics that had never before been linked so directly. Despite their name, black holes are among the brightest objects in the universe. The energy released as matter falls toward them can create quasars, blazing beacons visible across billions of light years. Quasars are powered by supermassive black holes consuming matter at a furious rate, producing light so intense that it can outshine all the stars in its host galaxy combined. These cosmic lighthouses allow astronomers to study the early universe, revealing how galaxies formed and evolved. Perhaps the most remarkable discovery of recent years came in 2015, when scientists detected gravitational waves for the first time, ripples in space-time itself, created by the collision of two black holes. These waves confirmed yet another prediction of Einstein's theory and opened an entirely new way of observing the universe. Through gravitational wave astronomy, humanity can now listen to the cosmic symphony of merging black holes, neutron stars, and other cataclysmic events, hearing the deep bass notes of space itself vibrating. Black holes challenge not only our scientific understanding, but also our imagination. They represent a frontier where physics reaches its limits, where time and space lose their familiar meaning, and where questions about the ultimate nature of reality become unavoidable. What happens inside a black hole's singularity? Could information ever escape, as some quantum theories suggest? Might black holes even be gateways to other universes, or the seeds of new ones? These are questions that scientists and philosophers alike continue to ponder, knowing that each answer will likely lead to deeper mysteries. In the end, black holes are reminders of the universe's dual nature, its beauty and its brutality, its order and its chaos. They are cosmic monsters that both consume and create, the silent anchors holding galaxies together, and the ultimate symbols of nature's power. In their darkness lies the light of understanding, for through studying them, humanity has come closer than ever to grasping the fundamental structure of reality. To look into a black hole is, in a sense, to look into the universe's own reflection, a mirror of infinity, where all beginnings and endings meet.
The future of humanity in space. For as long as humans have existed, we have looked up at the night sky and wondered what lies beyond. The stars have been our compass, our mythology, and our greatest mystery. But today, that ancient curiosity is no longer just a dream, it is a plan. The 21st century marks the dawn of a new age in which humanity begins its greatest journey, expanding beyond Earth to become a truly interplanetary species. The story of the future in space is one of ambition, courage, and technology, but also of survival. It is a vision shaped not only by wonder, but by necessity. Our planet, though breathtakingly beautiful, is fragile. Earth has given us everything: air to breathe, water to drink, and the foundation for all life. But it is vulnerable to both natural and human-made threats. Asteroid impacts, climate shifts, pandemics, and even our own industrial excesses remind us that no civilization lasts forever if confined to a single world. For humanity to endure for millennia, it must learn to live beyond its cradle. This realization has driven scientists, engineers, and dreamers to look toward the moon, Mars, and beyond, not just to explore, but to stay. The first steps in this new era began decades ago. The Apollo missions of the 1960s and 70s proved that humans could travel to another world and return safely. Yet those triumphs were followed by a long pause. For years, space exploration focused mainly on near-Earth orbit, constructing the International Space Station and advancing robotic missions to distant worlds. But a quiet revolution was brewing. In the early 21st century, private companies, SpaceX, Blue Origin, Virgin Galactic, and others transformed the landscape of spaceflight. What was once the domain of superpower nations became a field of open innovation. Reusable rockets, once dismissed as impossible, became a reality, slashing the cost of launching payloads into orbit and making regular access to space feasible for the first time in history. This technological leap has rekindled humanity's grandest aspirations. The moon, our closest neighbor, is once again a target, not for flags and footprints, but for permanence. NASA's Artemis program aims to return humans to the lunar surface and establish a sustainable presence there. The moon's south pole, with its shadowed craters containing frozen water, may one day support habitats, fuel production, and even agriculture. Water can be split into hydrogen and oxygen, the essential components of rocket fuel, turning the moon into a refueling station for missions deeper into space. Private companies are also racing to build lunar infrastructure, envisioning mining operations for rare metals and helium-3, a potential fuel for future fusion reactors. Beyond the moon lies Mars, the next great frontier. It is a world both alien and strangely familiar, with mountains taller than Everest, canyons deeper than any on Earth, and polar ice caps that shift with the seasons. Despite its barren surface, Mars offers the most promising home for humanity beyond Earth. It has water ice, day length similar to Earth's, and an atmosphere, thin and toxic by our standards, but present nonetheless. The challenge of reaching and colonizing Mars is immense,
Radiation exposure, low gravity, psychological strain, and the sheer distance from Earth make it one of the most daring ventures imaginable. Yet it is no longer a question of if, but when. SpaceX, under the vision of Elon Musk, has built the Starship rocket with the explicit goal of making humans multiplanetary. Each massive craft is designed to carry up to 100 people at a time, capable of landing on Mars, refueling there, and returning home. NASA's own plans complement this effort, with robotic precursors already exploring potential landing sites and testing technologies for in-situ resource utilization, the ability to make what we need from local materials. The first human missions to Mars are expected within the next couple of decades, and permanent bases may follow soon after. These early settlers will live in domed habitats or underground structures, shielded from radiation, growing food hydroponically, and recycling every drop of water. Over generations, humanity could learn to terraform small regions, warming the atmosphere and releasing trapped gases to thicken the air. While a fully Earth-like Mars remains centuries away, the first seeds of that transformation are already being imagined in laboratories today. But the future of humanity in space extends far beyond Mars. The outer solar system holds moons that could harbor life and resources beyond measure. Europa, one of Jupiter's moons, hides an ocean of liquid water beneath its icy crust, warmed by tidal forces. Enceladus, orbiting Saturn, sprays plumes of water vapor and organic molecules into space, suggesting hydrothermal activity below. These worlds may contain alien ecosystems, and studying them could answer one of science's most profound questions. Is life a rare miracle or a universal consequence of chemistry? Future missions, both robotic and crewed, may drill through the ice to explore these hidden oceans, carrying instruments designed to detect even the faintest traces of biology. Meanwhile, space habitats in orbit could become the first stepping stones toward permanent living beyond any planet. Visionaries such as physicist Gerard O'Neill once proposed enormous cylindrical colonies, worlds large enough to hold forests, rivers, and entire cities. With modern materials and technologies, such megastructures no longer seem impossible. Artificial gravity created through rotation, combined with solar energy and closed-loop ecosystems, could allow millions of people to live comfortably in space. These habitats might orbit Earth, the Moon, or even circle the Sun in vast networks, forming the first independent human civilizations beyond any planetary surface. The next century of space exploration will also redefine our relationship with energy and materials. Asteroid mining may become a cornerstone of the interplanetary economy. Many asteroids are rich in platinum, nickel, and other valuable metals, and some contain water that can be converted into fuel. Instead of launching heavy supplies from Earth, spacecraft could refuel in orbit or at mining stations scattered throughout the solar system. The economics of space could shift from scarcity to abundance, unlocking resources that could sustain civilization for millennia. Yet this future also demands responsibility. Expanding into space is not merely a technical challenge, it is an ethical one. How should humanity protect the pristine environments of other worlds? Should Mars be terraformed if it means destroying possible native life? Who owns the Moon, the asteroids, or the resources of space? International treaties like the Outer Space Treaty of 1967 established the principle that no nation can claim celestial bodies. But as private companies and nations compete, the rules of the new frontier will need constant refinement to ensure cooperation rather than conflict. The cultural impact of becoming a spacefaring species will be profound. The first children born on Mars will never know an Earth sky. Their sense of home, gravity, and even humanity will be shaped by life under a crimson sun. New art, music, and philosophies will emerge, influenced by the view of two moons instead of one. The human story, once confined to a single planet, will unfold across multiple worlds. Even further ahead lies interstellar exploration, the dream of reaching other star systems. At present, the distances are staggering. The nearest star, Proxima Centauri, lies over 4 light-years away, a journey that would take tens of thousands of years with current propulsion technology. Yet scientists are developing new ideas: fusion propulsion, antimatter engines, and even laser-powered light sails that could push small probes to a fraction of light speed. Projects like Breakthrough Starshot aim to send tiny spacecraft to neighboring stars within a single human lifetime. Though these missions will begin as robotic explorers, they are the first steps toward one day carrying human passengers beyond the solar system, perhaps to the exoplanets we already know exist. The future of humanity in space is not simply about reaching other worlds, it is about ensuring the survival and flourishing of our species. It is about curiosity, courage, and the unyielding human spirit that refuses to stop exploring. Just as our ancestors crossed oceans and continents, future generations will cross the void between worlds, carrying with them the memory of Earth, the blue cradle that first gave us life. From lunar colonies to Martian cities, from orbital habitats to interstellar voyages, our destiny is no longer confined to one planet. Humanity stands on the edge of a cosmic horizon, ready to take its next great leap. And when future historians look back, they will see this moment, the moment we reached for the stars, not as the end of our story on Earth, but as the beginning of our story in the universe.
Asteroids, comets, and cosmic threats. Across the black expanse of space, millions of silent, remained fragments. Those fragments are what we now call asteroids. Most asteroids are found in the asteroid belt, a vast region between Mars and Jupiter where countless rocky bodies orbit the Sun. Though often imagined as tightly packed, the belt is mostly empty space. The asteroids within it are separated by millions of miles. They range in size from Ceres, a dwarf planet nearly 600 miles across, to pebbles smaller than a grain of sand. These objects are composed largely of rock and metal, the same materials that form the inner planets, and their surfaces are scarred by billions of years of collisions. Each impact, each fragment, tells the story of a solar system still in motion. Comets, by contrast, come from the cold, distant reaches far beyond Neptune. They are composed of ice, dust, and organic molecules, the frozen remnants of the solar system's outer regions. When a comet ventures close to the Sun, its icy surface begins to vaporize, releasing gas and dust that form the glowing coma and long shimmering tail that have inspired awe since ancient times. Early civilizations viewed comets as omens of doom or divine messages, and it was only in the modern era that scientists came to understand them as natural, predictable phenomena governed by the same physical laws as planets. While asteroids and comets have different origins, their orbits sometimes intersect with Earth's. When they do, they become what astronomers call near-Earth objects, or NEOs. Most of these pass harmlessly at vast distances, but every so often, one comes too close for comfort. The scars of such encounters are written in the geological record of our planet. 66 million years ago, an asteroid, roughly 6 miles wide, struck what is now the Yucatan Peninsula, unleashing an explosion equal to billions of nuclear bombs. The impact carved out the Chicxulub crater, darkened the skies with debris, and triggered a mass extinction that wiped out 3/4 of all life on Earth, including the dinosaurs. That single event reshaped evolution, clearing the path for mammals and ultimately humans to rise. Smaller impacts have also left their mark. The Barringer crater in Arizona, a mile wide and 600 feet deep, was formed 50,000 years ago by a nickel-iron meteorite barely 150 feet across. In 1908, a powerful explosion flattened over 800 square miles of Siberian forest near the Tunguska River, likely caused by an asteroid fragment exploding in the atmosphere. Even in recent decades, near misses and smaller impacts have reminded scientists of how vulnerable Earth remains.
In 2013, a 20-meter meteor exploded over Chelyabinsk, Russia, with a force 30 times greater than the atomic bomb dropped on Hiroshima. The shockwave shattered windows across an entire city, injuring over 1,000 people. These events make one thing clear. Asteroids and comets are not relics of the distant past. They are part of Earth's ongoing relationship with the solar system. For this reason, astronomers around the world now track the skies with relentless vigilance. NASA's Planetary Defense Coordination Office, founded in 2016, is dedicated to identifying and monitoring near-Earth objects that could pose a threat. Telescopes such as Pan-STARRS in Hawaii and the Catalina Sky Survey in Arizona scan the heavens nightly, cataloging thousands of new asteroids every year. Advanced algorithms predict their orbits decades into the future, calculating potential impact risks with extraordinary precision. But detection is only the first step. Humanity has also begun experimenting with ways to deflect or destroy dangerous objects before they strike. In 2022, NASA's DART mission, the Double Asteroid Redirection Test, made history by deliberately crashing a spacecraft into a small asteroid named Dimorphos to test if its orbit could be changed. The impact successfully altered the asteroid's trajectory, marking the first time humans had ever changed the motion of a celestial body. It was a quiet but monumental achievement, proving that planetary defense is not just science fiction. Future missions may use kinetic impactors, gravity tractors, or even laser ablation to nudge hazardous asteroids safely away from Earth. While large impacts are rare, they hold catastrophic potential. A rock even half a mile wide could destroy entire regions and cause global climate disruption through dust and soot that blocks sunlight. For this reason, international cooperation is essential. Agencies in the United States, Europe, and other nations share data and strategies to ensure early warning and coordinated response. Plans include evacuation protocols, impact simulations, and public education about the difference between realistic threats and sensational rumors. The goal is not to live in fear of the sky, but to understand and prepare for its dangers. Yet asteroids and comets are not only threats, they are also opportunities. These ancient bodies hold immense scientific and economic value. They contain pristine material from the dawn of the solar system, offering clues about how planets and life began. Missions such as Japan's Hayabusa and NASA's OSIRIS-REx have already collected samples from near-Earth asteroids, revealing complex chemistry and even traces of organic compounds, the very ingredients of life. Some scientists believe that much of Earth's water and organic matter may have arrived through impacts with comets and carbon-rich asteroids billions of years ago. If true, then the same forces that can destroy worlds may also have seeded them with the elements of creation. Beyond science, asteroids could one day fuel the next phase of human expansion. Many are rich in metals such as platinum, nickel, and iron, and others contain vast reserves of water ice that could be turned into rocket fuel. Mining these bodies could support space colonies, power stations, and deep space missions, freeing humanity from the resource limits of Earth. What were once seen as cosmic threats may become stepping stones for our survival among the stars. In the end, asteroids and comets embody both sides of nature's coin, destruction and renewal. They remind us of how precarious life can be, yet also how deeply connected we are to the cosmos. The same celestial fragments that once rained devastation upon Earth also delivered the materials that made life possible. Every night, as we watch a meteor streak across the sky, we are witnessing the remnants of that ancient process. Bits of cosmic debris burning away in the atmosphere, symbols of both peril and beauty. The universe, vast and indifferent, does not promise safety. But with knowledge, vigilance, and ingenuity, humanity can face its cosmic environment not as helpless observers, but as active participants. Asteroids and comets are no longer just harbingers of doom. They are reminders of our origins and testaments to our resilience.
In understanding them, we learn not only how to protect our world, but also how to take our place among the stars.
The secrets of the sun. At the center of our solar system burns an ancient and relentless fire, the sun, a colossal sphere of plasma that has sustained life on Earth for more than 4.5 billion years. It is at once familiar and mysterious, the golden heart of our sky and the cosmic engine upon which every heartbeat, every leaf, and every breath depends. From its blinding light to its invisible radiation, the sun governs the rhythm of our planet, shaping weather, climate, and even the course of evolution itself. Yet, for all its apparent constancy, the sun is not a calm or eternal presence. It is a living star, seething with magnetic storms, burning through unimaginable energy, and destined, one distant day, to fade and die. To grasp the sun's nature, one must imagine a sphere nearly 110 times wider than Earth, containing more than 99% of the solar system's total mass. Its core, where nuclear fusion occurs, reaches temperatures of over 27 million degrees Fahrenheit. Under this crushing heat and pressure, hydrogen atoms fuse to form helium, releasing tremendous amounts of energy in the process. Every second, the sun converts roughly 600 million tons of hydrogen into helium, and in doing so, it releases energy equivalent to billions of nuclear bombs. This energy radiates outward, eventually emerging as the sunlight that warms our planet. Without this steady flow of fusion, life as we know it could not exist. The sun is structured in layers, each performing a crucial role in this cosmic machine. At the core lies the fusion engine, surrounded by the radiative zone, where energy slowly migrates outward through countless collisions between photons and charged particles. It can take a single photon thousands or even millions of years to escape this region. Beyond that lies the convective zone, where immense columns of hot plasma rise and cool in turbulent motion, creating the granulated texture visible on the sun's surface. The visible surface itself, called the photosphere, glows at nearly 10,000 degrees Fahrenheit, the light we see with our eyes. Above it shimmered the chromosphere and the corona, ethereal layers of superheated gas extending millions of miles into space. During a total solar eclipse, when the moon blocks the photosphere's glare, the corona becomes visible, a ghostly white halo that reveals the sun's hidden power. The sun's behavior is governed not only by heat and pressure, but by magnetism. It possesses a vast and complex magnetic field that twists, folds, and tangles as the star rotates. Every 11 years or so, the sun's magnetic poles reverse, and its activity intensifies in what scientists call the solar cycle. During these periods, dark sunspots appear, regions of intense magnetic concentration that are cooler than their surroundings. Around them, vast eruptions occur, solar flares that release bursts of radiation, and coronal mass ejections, colossal clouds of plasma hurled into space at millions of miles per hour. These outbursts are not confined to the sun's domain. They reach Earth in the form of solar storms, capable of disrupting satellites, radio communications, and even electrical power grids. In March of 1989, a powerful solar storm struck Earth's magnetosphere, knocking out power across the Canadian province of Quebec for 9 hours and damaging transformers across North America. Such events reveal the sun's capacity to influence not just nature, but modern civilization itself. Our planet is shielded by its magnetic field and atmosphere, which deflect most of the harmful radiation. But a storm of sufficient strength could cause catastrophic failures in a world dependent on satellites and electronics. To anticipate these dangers, scientists monitor the sun with a fleet of space observatories, including NASA's Solar Dynamics Observatory and the Parker Solar Probe, which in 2021 became the first spacecraft to actually fly through the sun's corona, sampling its plasma directly. Despite its destructive potential, the sun is also the reason Earth is habitable. Its light drives photosynthesis, fueling the food chain from the smallest plant to the largest predator. Its warmth maintains liquid water, and its gravitational pull stabilizes our planet's orbit. Subtle variations in the sun's output over geological timescales have influenced climate, triggering ice ages and warm periods. But the stability of the sun over billions of years is what allowed life to emerge and flourish. Compared to many stars, it is remarkably calm, a yellow dwarf of spectral type G2V, quietly burning in middle age. It is neither too large to explode violently, nor too small to fade into obscurity too soon. In the vast diversity of stellar possibilities, the sun represents a rare and delicate balance. Yet, even disbalance cannot last forever. The sun is roughly halfway through its life cycle. In about 5 billion years, its supply of hydrogen fuel will begin to dwindle. As fusion slows in the core, gravity will compress the sun inward until new fusion reactions ignite in its outer layers. The result will be dramatic. The sun will swell into a red giant, expanding beyond the orbit of Mercury and possibly engulfing Venus and Earth. The surface will cool to a deep crimson, while the outer layers drift away into space as a vast shell of glowing gas. For a brief time, this planetary nebula will shimmer like a cosmic flower, marking the sun's final act as a living star. The core that remains will collapse into a white dwarf, a dense ember about the size of Earth but with half the sun's original mass, slowly fading over trillions of years until it becomes a cold, dark remnant. Though that distant transformation lies far beyond human timescales, understanding it gives us perspective on our place in the universe. The same fusion that powers the sun's gentle light also fuels the violent births and deaths of stars across the cosmos. Every atom of carbon, oxygen, and iron in our bodies was once forged in the heart of some long-dead star. The sun, like all stars, is both a destroyer and a creator, a link in the endless cycle of cosmic evolution. Modern science continues to unveil the sun's mysteries. Through space missions, computer simulations, and laboratory plasma experiments, researchers are piecing together the complex dynamics of stellar magnetism and fusion. The Parker Solar Probe and the European Space Agency's Solar Orbiter are revealing how energy and matter flow from the sun into space, driving the solar wind that fills the entire solar system. Each discovery deepens our understanding not only of our star, but of the countless others that fill the galaxy. The sun's brilliance has inspired awe since the dawn of humanity. Ancient civilizations worshipped it as a god, recognizing instinctively its vital role in sustaining life. To the Egyptians, it was Ra, the divine charioteer crossing the sky. To the Greeks, it was Helios, radiant and eternal. Today, we no longer bow before the sun in reverence, but we still depend upon it completely. Its energy powers our ecosystems, our technology, and our very existence. Even as we dream of distant worlds and other stars, we remain children of this light. When we look up at a sunrise, we are seeing the work of nuclear fire so intense that even a fraction of its output could destroy a world, yet so stable that it has nurtured ours for eons. The sun is not just the center of our solar system, it is the source of everything we know. Its light is ancient, its power eternal in human terms, and its story, from fiery birth to quiet death, is the story of all stars.
To study the sun is to study the forces that made the universe itself. And though one day it will fade, the echoes of its warmth will continue in the life and legacy it leaves behind, in every living thing on Earth, and in every dream of the stars that its light inspires.
The expanding universe. From the moment humanity first looked up at the night sky, the universe appeared timeless, a vast, unchanging sea of stars spread across eternity. For millennia, it seemed logical to believe that the cosmos was static, infinite, and eternal. Yet in the last century, science has revealed a truth far stranger and more profound. The universe is not standing still. It is growing, stretching, and evolving. Space itself is expanding, carrying galaxies away from one another like dots on the surface of an inflating balloon. This revelation forever altered our understanding of reality, showing that the cosmos had a beginning, that it has a history, and that it may one day meet an end. The story of the expanding universe begins with a simple but revolutionary insight, that the light from distant galaxies is redshifted. When astronomers observe these galaxies, they find that their spectral lines, the fingerprints of the elements they contain, are shifted toward longer, redder wavelengths. This effect is not due to the galaxies moving through space like projectiles. Rather, it is because space itself is stretching, causing the light waves traveling through it to elongate. This discovery, made in the early 20th century by Edwin Hubble and Vesto Melvin Slipher, became one of the most profound findings in the history of science. It meant that the universe was not static, but expanding in all directions, implying that in the distant past, everything must have been closer together, denser, hotter, and unimaginably small. This realization gave rise to the Big Bang theory, the modern explanation for the universe's origin. According to this model, about 13.5 billion years ago, all matter, energy, space, and even time itself were compressed into a singular point, a state of infinite density and temperature. Then, in an instant, the universe began to expand. It was not an explosion in space, but an expansion of space itself, a transformation in which the very fabric of reality began to stretch. In the first fractions of a second, the universe underwent a period of cosmic inflation, expanding exponentially faster than the speed of light. Quantum fluctuations, tiny ripples in the energy field, were stretched across the cosmos, seeding the large-scale structures that would one day become galaxies and clusters. As the universe cooled, energy condensed into matter. Protons and neutrons formed within minutes, combining to create the first atomic nuclei in a process known as primordial nucleosynthesis. After roughly 380,000 years, the universe cooled enough for electrons to bind to nuclei, forming the first neutral atoms, mostly hydrogen and helium. With matter and radiation decoupled, light was finally free to travel, creating the cosmic microwave background, a faint afterglow that still fills the universe today. This radiation, discovered by Arno Penzias and Robert Wilson in 1965, is a direct echo of the Big Bang, providing a snapshot of the universe when it was less than 400,000 years old. It is one of the most powerful pieces of evidence that our universe had a beginning. As billions of years passed, gravity began to pull matter together, forming the first stars and galaxies. Within these stellar furnaces, hydrogen fused into heavier elements, creating the building blocks of planets, life, and everything we see around us. Galaxies grouped into clusters, clusters into superclusters, and filaments of dark matter formed the cosmic web, an immense structure spanning billions of light years, linking galaxies across the universe like threads of light in a boundless tapestry.
And all the while, space continued to expand, carrying these galaxies farther apart. For much of the 20th century, astronomers believed that this expansion must be slowing down. Gravity, after all, should tug everything inward. If there was enough matter, perhaps the universe would one day stop expanding and collapse back in on itself in a big crunch. But in the late 1990s, two independent teams studying distant supernovae made a stunning discovery. The universe's expansion is not slowing down, it is accelerating. Some mysterious force is pushing galaxies apart faster and faster. This unknown phenomenon became known as dark energy, a term that describes our ignorance more than our understanding. It appears to make up about 70% of the universe's total energy content, yet its true nature remains one of the greatest mysteries in modern physics. To explain dark energy, scientists have proposed several theories. One suggests that it is a property of space itself, the cosmological constant first introduced and later discarded by Albert Einstein. Another idea is that dark energy arises from a dynamic field that changes over time, similar to the Higgs field that gives particles mass. Whatever its source, dark energy dominates the large-scale behavior of the universe, determining its ultimate fate. If the expansion continues to accelerate indefinitely, galaxies will drift farther apart until they are forever isolated, their light fading from view. Over trillions of years, stars will burn out, black holes will evaporate, and the cosmos will fade into a cold, dark void, a fate known as the Big Freeze. Other possibilities exist. If dark energy were to grow stronger over time, the acceleration could become so extreme that it tears apart galaxies, stars, and even atoms in a catastrophic event called the Big Rip. Alternatively, if dark energy changes sign or weakens, gravity could regain control, halting the expansion and triggering a collapse back into a fiery singularity, a rebirth in the form of another Big Bang. These ideas remain speculative, but they reveal how little we truly know about the cosmic forces that shape existence. Beyond dark energy lies another enigma: dark matter. Though invisible and undetectable by ordinary means, it reveals its presence through gravity. Galaxies spin too fast for their visible matter alone to hold them together. Something unseen provides the extra mass needed to keep them intact. This mysterious substance, thought to make up about 27% of the universe, does not emit or absorb light, and its composition remains unknown. Together, dark matter and dark energy account for roughly 95% of the universe, leaving the familiar atoms that make up stars, planets, and people as only a tiny fraction of the cosmic total. In essence, we live in a universe we barely understand, surrounded by forces we can measure but cannot yet explain. Despite these mysteries, humanity has made extraordinary progress in mapping the cosmos. The Hubble Space Telescope has peered into the farthest reaches of space, revealing galaxies so distant that their light began its journey soon after the Big Bang. Its successor, the James Webb Space Telescope, is pushing even deeper, capturing the faint glow of the first galaxies that formed more than 13 billion years ago. Through these instruments, astronomers are not merely observing space, they are looking back in time, witnessing the universe as it was in its infancy. Each discovery reshapes our understanding of where we come from. The expanding universe tells us that everything, every star, planet, and living being emerged from a single, shared origin. The elements forged in ancient stars were scattered across space, gathered into new worlds, and eventually into us. We are, quite literally, made of the universe itself, a product of its expansion, its evolution, and its continuing story.
To grasp the enormity of this idea is to feel both small and infinite at once. The expansion of the universe is not something that happened long ago. It is happening now, in every direction, in every moment. Galaxies billions of light years away continue to recede, their light stretched thinner and redder as space grows between us. Even the atoms in our bodies drift infinitesimally apart as the fabric of reality stretches. We live within the flow of cosmic expansion, carried along by the same force that began with the birth of time itself. In contemplating the expanding universe, we confront both the majesty and the impermanence of all things. Everything we know, from the smallest grain of dust to the largest galaxy cluster, exists in motion, shaped by the relentless unfolding of space. The universe is not a static backdrop, but a living, changing entity, a cosmic story still being written. And though its scale defies comprehension, its origin is bound to ours. We are part of that story, witnesses to an expansion that began long before us and will
long after the last star fades into the dark. The search for alien life. For as long as humans have gazed at the night sky, one question has haunted and inspired us more than any other. Are we alone in the universe? The search for alien life is one of the greatest scientific and philosophical pursuits of our time, a quest that reaches from the depths of Earth's oceans to the edges of the cosmos. It bridges disciplines, blending biology, chemistry, astronomy, and technology in a single effort to uncover whether life is a rare miracle confined to Earth or a cosmic inevitability written into the fabric of the universe itself. At its core, this search begins with a simple truth. Life as we know it depends on a few universal ingredients: water, organic molecules, and energy. If those conditions can exist elsewhere, then life may as well. The discovery of planets orbiting other stars, once only a dream, has transformed this question from speculation into science. In the past few decades, astronomers have identified thousands of exoplanets, many located within the so-called habitable zone, where temperatures could allow liquid water to exist on their surfaces. These worlds range from Earth-sized planets circling red dwarfs to massive gas giants with moons that might harbor hidden oceans. Each discovery expands our understanding of what is possible, suggesting that our planet may not be the only oasis in a cosmic desert. But the search for life began much closer to home. Within our own solar system, there are worlds that seem barren at first glance, but may conceal the potential for biology. Mars, long imagined as a place of canals and civilizations, has captured scientific attention for decades. Robotic explorers like NASA's Perseverance and Curiosity rovers have uncovered evidence that Mars once had rivers, lakes, and perhaps even a vast northern ocean. Ancient minerals and sedimentary layers point to a time when the red planet's surface was warm and wet, conditions that could have supported microbial life. Today, Mars is cold and dry, yet beneath its rusty surface, frozen water and subsurface brines may still persist. Scientists are now searching for signs of fossilized microbes or chemical traces of ancient life that may have endured long after the planet's surface became hostile. Beyond Mars lie worlds even more promising. Europa, one of Jupiter's moons, is encased in ice but believed to hide a global ocean beneath its surface, an ocean containing more water than all of Earth's seas combined. Geysers of water vapor erupt from cracks in the ice, suggesting that the ocean below may be in contact with the moon's rocky mantle, where heat and minerals could provide the energy needed for life to thrive. Similarly, Saturn's moon, Enceladus, has revealed towering plumes of water vapor and organic compounds venting into space. When the Cassini spacecraft flew through these plumes, it detected hydrogen and complex molecules, a possible signature of hydrothermal activity on the ocean floor, the very kind of environment where life began on Earth. These findings have redefined what we consider habitable, showing that life might exist not only on planets, but on icy moons orbiting far from the Sun. Even more surprising are the possibilities found on worlds that seem utterly alien. Titan, another of Saturn's moons, has lakes of liquid methane and ethane on its surface. Though far too cold for water-based life, Titan possesses a rich chemistry of organic molecules, hinting that life might not always need water, that it could emerge in forms completely unfamiliar to us. If biology can adapt to conditions as extreme as those on Titan, then the range of potential habitats in the universe is far broader than we once imagined. While robotic missions search for evidence within our solar system, astronomers are turning their attention outward, scanning distant exoplanets for signs of habitability. The James Webb Space Telescope has opened a new era in this search by analyzing the atmospheres of alien worlds. By studying how starlight filters through a planet's atmosphere during transit, scientists can detect the fingerprints of gases such as oxygen, methane, and carbon dioxide. On Earth, these molecules are maintained by biological activity. Their simultaneous presence could signal that something is alive. This approach, known as biosignature detection, may soon allow humanity to identify the first truly Earth-like planet beyond our solar system. Yet the search for life is not limited to biology as we know it. The field of astrobiology explores the limits of existence in extreme environments, from boiling acid pools and deep-sea vents to frozen deserts and radioactive caves. On Earth, microbes known as extremophiles have been found thriving in places once thought utterly lifeless. They feed on sulfur near volcanic vents, endure radiation that would kill most organisms, and survive temperatures far below freezing. These discoveries have shattered old assumptions, showing that life is far more adaptable and resilient than we ever imagined. If microbes can flourish in such extremes here, why not on Mars, Europa, or even beneath the icy crust of Pluto? The search for alien life also extends beyond biology to technology. Since the mid-20th century, scientists have listened for radio signals from other civilizations through programs such as SETI, the search for extraterrestrial intelligence. Using massive radio telescopes, researchers have scanned the heavens for narrowband transmissions that could indicate artificial origins. Though no confirmed signals have been found, the search continues, fueled by both curiosity and humility. In recent years, advances in artificial intelligence and computing have allowed astronomers to sift through vast datasets more efficiently than ever before, increasing the odds that a faint whisper from another world might one day be heard. Some scientists go further, proposing that alien civilizations might not use radio at all. They might communicate with lasers, neutrinos, or forms of technology beyond our understanding. Others suggest that evidence of advanced life might be visible in the form of megastructures, vast artificial constructs that harness the energy of stars, known as Dyson spheres. None have been detected, but the search itself reflects the boundless scope of human imagination and the deep longing to know whether consciousness exists elsewhere. Philosophically, the implications of finding alien life are immense. Even the discovery of simple microbes on another world would transform our understanding of biology, suggesting that life is a common outcome of planetary evolution rather than a rare accident. It would mean that the universe is teeming with possibilities, that wherever conditions are right, life finds a way.
The discovery of intelligent life, on the other hand, would challenge every assumption about our place in the cosmos. It would redefine religion, philosophy, and perhaps even our sense of destiny. Humanity, long accustomed to seeing itself as unique, would suddenly confront the reality that we are one of many voices in a cosmic chorus. For now, the silence of the stars endures. Despite decades of searching, no clear signal has reached us, no alien artifact has been found, and no probe has arrived from distant worlds. This absence of evidence is sometimes called the Fermi paradox, the contradiction between the high probability of extraterrestrial civilizations and the lack of any sign of them. Perhaps intelligent life is exceedingly rare, or perhaps civilizations destroy themselves before mastering interstellar travel. It may be that communication across such vast distances is impossible, or that the universe is simply too young for many civilizations to have arisen. Or more hauntingly, perhaps they are out there, but we have not yet learned how to listen. Still, the search continues, in laboratories, in observatories, and in the imaginations of those who look up at the stars and wonder. Each new mission, each telescope, and each discovery brings us closer to answering the question that defines our place in the universe. Whether life exists elsewhere or not, the pursuit itself has changed us. It has taught us that Earth is not the center of creation, but a single, fragile world adrift in a vast and living cosmos. In the end, the search for alien life is as much about understanding ourselves as it is about finding others. It forces us to confront what life means, what intelligence is, and how precious our existence truly is. As we listen to the silent expanse of the universe, we are reminded that every form of life, from the simplest microbe to the most complex civilization, is part of the same cosmic story. And whether
Satellites and space technology. Above Earth's blue horizon, a silent armada circles the planet. Thousands of satellites orbiting in disciplined precision, each one a vital link in the chain that connects our modern world. They are the unseen infrastructure of civilization, carrying the invisible threads of communication, navigation, weather forecasting, defense, and science that bind together our daily lives. From the moment we wake to check the morning forecast, to the instant we navigate a route, stream a movie, or transmit data across continents, we are dependent on these machines. Satellites have turned space from a realm of mystery into a working frontier, one that humankind not only explores, but actively inhabits. The story of satellites begins with an idea that once seemed impossible. In the mid-20th century, when the world was divided by the tensions of the Cold War, a group of scientists envisioned sending artificial objects into orbit to observe Earth and communicate across vast distances. That dream became reality on October 4, 1957, when the Soviet Union launched Sputnik 1, a polished aluminum sphere no larger than a beach ball, transmitting a steady radio pulse as it circled the globe every 96 minutes. Though its signal was simple, its impact was profound. Humanity had placed its first emissary in space, proving that Earth could be observed from above and inaugurating a new age of science, technology, and geopolitics. The United States responded swiftly, launching its own satellite, Explorer 1, in early 1958. This small craft carried scientific instruments that discovered the Van Allen radiation belts, zones of charged particles trapped by Earth's magnetic field. In the years that followed, satellites multiplied rapidly, each one more advanced, more specialized, and more ambitious than the last. The early era of space exploration was driven by rivalry, but it soon gave rise to cooperation, laying the foundation for the global systems that now define daily life on Earth. Today, satellites fall into several broad categories, each serving a unique purpose. Communication satellites form the backbone of global connectivity. They relay television broadcasts, telephone calls, internet data, and emergency signals across continents and oceans.
Positioned in geostationary orbit, about 22,000 miles above the equator, these satellites appear motionless in the sky, matching Earth's rotation so that antennas on the ground can maintain constant alignment. Without them, international broadcasting, live global events, and worldwide internet service would not exist. Navigation satellites, such as those in the Global Positioning System, GPS, revolutionized the way humanity moves through the world. First developed by the U.S. Department of Defense in the 1970s, GPS now forms the basis of a global network used for everything from aviation and maritime operations to agriculture, logistics, and everyday driving. It relies on precise timing signals transmitted from at least 24 satellites, allowing receivers on Earth to calculate their location with astonishing accuracy. Other nations have since built their own systems: Russia's GLONASS, Europe's Galileo, and China's Beidou, ensuring that navigation from space remains a universal utility. Weather satellites are another triumph of space technology, offering humanity a god's-eye view of the atmosphere. They monitor cloud patterns, track hurricanes, measure ocean temperatures, and detect environmental changes with a precision unimaginable a century ago. The first of these, TIROS-1, launched in 1960, sent back grainy images of Earth's cloud cover, revolutionizing meteorology. Today's satellites, such as the GOES series and Europe's Meteosat, provide real-time data that saves countless lives by predicting storms, floods, and heat waves before they strike. They also play a crucial role in studying climate change, monitoring melting ice caps, rising sea levels, and shifting weather patterns across the globe. Beyond these practical systems, scientific satellites have expanded our understanding of the cosmos itself. The Hubble Space Telescope, launched in 1990, transformed astronomy by capturing breathtaking images of galaxies, nebulae, and distant stars with unprecedented clarity. Orbiting above the distortion of Earth's atmosphere, Hubble revealed a universe far more vast and dynamic than ever imagined. Its successors, such as the James Webb Space Telescope, now peer even deeper into cosmic history, studying light that has traveled for billions of years to reach us. Closer to home, satellites like the Chandra X-ray Observatory, the Solar Dynamics Observatory, and the Laser Interferometer Space Antenna, LISA, continue to explore the hidden forces that govern the universe, from black holes to gravitational waves. But not all satellites are large government-funded projects. In recent years, technological advances have made it possible for private companies, universities, and even individuals to launch small satellites known as CubeSats. These compact, low-cost devices are transforming space research by democratizing access to orbit. They are used for everything from monitoring crops and tracking wildlife to conducting scientific experiments and providing internet coverage to remote regions. Mega constellations, fleets of thousands of satellites like those operated by SpaceX's Starlink or Amazon's Project Kuiper, aim to blanket the globe with high-speed internet, bridging the digital divide and bringing connectivity to every corner of the planet. Yet this new era of abundance brings new challenges. The rapid proliferation of satellites has led to growing concern over space debris, fragments of defunct spacecraft and spent rocket stages that orbit Earth at thousands of miles per hour. Even a small piece of debris can destroy an operational satellite upon impact. There are now more than 100 million pieces of debris larger than a millimeter circling the planet, creating what scientists call the Kessler syndrome, a cascading effect where collisions generate more debris, increasing the risk of further collisions. To prevent this, international organizations and space agencies are developing strategies to remove or deorbit defunct satellites, enforce stricter launch regulations, and ensure that the space above Earth remains sustainable for future generations. Despite these risks, the benefits of satellite technology are immeasurable. They are indispensable tools for disaster response, environmental monitoring, and global communication. When wildfires rage, satellites map the spread of flames. When earthquakes strike, they assess damage and guide rescue teams. They track deforestation, illegal fishing, and pollution, giving scientists and policymakers the data needed to protect the planet. In this way, satellites have become not only instruments of convenience, but guardians of Earth itself. The technological sophistication of these machines is staggering. Each satellite must survive the violent forces of launch, the vacuum of space, extreme temperature changes, and years of radiation exposure. They are built with meticulous precision, equipped with solar arrays that convert sunlight into power and systems that can operate autonomously for decades. Engineers design them with fail-safes, redundancy, and advanced communication systems that allow operators to control them from thousands of miles away. The fact that such fragile creations can orbit Earth with accuracy measured in inches is a testament to human ingenuity and persistence. Despite these risks, the benefits of satellite technology are immeasurable. They are indispensable tools for disaster response, environmental monitoring, and global communication. When wildfires rage, satellites map the spread of flames. When earthquakes strike, they assess damage and guide rescue teams. They track deforestation, illegal fishing, and pollution, giving scientists and policymakers the data needed to protect the planet. In this way, satellites have become not only instruments of convenience, but guardians of Earth itself. Looking ahead, the role of satellites will only grow more essential. Future generations of spacecraft will form vast networks powered by artificial intelligence, capable of self-organizing and adapting to changing conditions. Some will orbit the Moon and Mars, supporting human exploration beyond Earth. Others will serve as platforms for clean energy transmission, space-based manufacturing, or planetary defense. Already, NASA and private companies are testing solar power satellites that could beam energy directly to Earth, potentially transforming global energy production. In a broader sense, satellites symbolize humanity's transition from passive observers of space to active participants in it. They are extensions of our senses and our will, instruments that allow us to see, measure, and understand the planet we inhabit, and to glimpse the universe beyond. In a single generation, we have filled the heavens with our creations, creating a technological constellation that mirrors the stars themselves. When we look up at the night sky, few of those glittering points are natural anymore. Some are moving lights, reflections from the machines we have sent aloft. They mark the presence of human thought orbiting far above, circling endlessly through the void. The satellites that once symbolized national pride now represent global interconnection, a web of intelligence surrounding our world. In them, we see both the triumph and the responsibility of our species, proof that humanity, once bound to the surface of Earth, has truly become a civilization of the sky.
The future of space exploration. Humanity stands at the threshold of a new cosmic era, one defined not by the question of whether we can explore space, but by how far and how wisely we will go. For the first time in history, space is no longer the exclusive domain of governments or scientists. It has become a shared frontier, one where nations, private companies, and even individuals collaborate to push the limits of what is possible. The dream of exploring the stars, once confined to the imagination of visionaries like Konstantin Tsiolkovsky, Wernher von Braun, and Carl Sagan, is now transforming into a living, tangible enterprise. The future of space exploration promises to redefine not only our technology, but our very understanding of what it means to be human in the cosmos. At the heart of this transformation is a profound shift in motivation. The space race of the 20th century was driven by competition, a geopolitical contest between superpowers seeking dominance beyond Earth. But the 21st century has given rise to a new paradigm: cooperation, innovation, and long-term sustainability. Humanity's new space age is being built not on rivalry, but on partnership. Space agencies such as NASA, the European Space Agency, Roscosmos, JAXA, and ISRO now work together alongside private enterprises like SpaceX, Blue Origin, and Rocket Lab. This collaboration is paving the way for missions that would have been unimaginable just a few decades ago. Permanent bases on the Moon, crewed expeditions to Mars,
robotic explorers venturing into the icy moons of Jupiter and Saturn, and telescopes capable of observing the birth of the first galaxies. The moon is humanity's next great milestone. Once the battleground of Cold War prestige, it is now viewed as a gateway to the broader solar system. NASA's Artemis program, named after the twin sister of Apollo, aims to return humans to the lunar surface, this time to stay. Unlike the brief Apollo visits of the 1960s and 70s, Artemis seeks to establish a sustainable lunar presence, complete with habitats, power systems, and research facilities. The moon will serve as a testing ground for life support systems, autonomous construction technologies, and resource utilization, skills essential for venturing further outward. Scientists hope to extract water ice from the lunar poles, using it to produce oxygen and rocket fuel. This single breakthrough could transform the moon into a refueling station for missions bound for Mars and beyond, reducing the cost and complexity of deep space travel. Mars, long regarded as the next great destination, represents the most ambitious goal of human exploration. Robotic missions have already laid the groundwork. Orbiters like Mars Reconnaissance Orbiter and rovers like Curiosity, Perseverance, and Zhurong have mapped its terrain, analyzed its rocks, and confirmed the presence of ancient riverbeds and frozen water. The data they send back suggests that Mars once possessed conditions suitable for life. Future missions aim to bring back samples from its surface, and within the next few decades, the first human explorers may step onto its dusty plains. Colonizing Mars will be one of humanity's greatest challenges. Its thin atmosphere, intense radiation, and frigid temperatures will demand revolutionary advances in engineering, medicine, and closed-loop ecology. Yet the rewards are profound: a second home for humanity, and perhaps the first step toward becoming a multi-planetary species. Beyond Mars lies the realm of the outer planets, where robotic explorers continue to expand our understanding of the solar system's diversity. The icy moons of Jupiter and Saturn, Europa, Ganymede, Titan, and Enceladus have captured particular interest. Beneath their frozen crusts, vast oceans of liquid water may conceal conditions hospitable to life. Missions like NASA's Europa Clipper and ESA's JUICE are designed to explore these alien oceans, searching for signs of biological activity. Farther still, probes may one day visit Uranus and Neptune, worlds of gas and mystery that remain largely unexplored. Each mission adds a new chapter to humanity's growing cosmic story, revealing that the solar system is not a collection of dead rocks, but a dynamic, living environment shaped by forces both familiar and strange. The future of space exploration is also being transformed by technological revolutions here on Earth. Reusable rockets, pioneered by companies like SpaceX, have drastically reduced launch costs, making access to space more affordable than ever before. Advanced propulsion technologies, including nuclear thermal engines, solar sails, and ion thrusters, promise to shorten travel times to distant worlds. Artificial intelligence and robotics are enabling spacecraft to operate autonomously in environments too dangerous or distant for human control. Onboard AI systems can analyze data, make decisions, and even repair equipment, allowing probes to explore the outer reaches of the solar system without direct human guidance. Meanwhile, the emergence of commercial spaceflight is redefining who can go to space. Companies like SpaceX, Blue Origin, and Virgin Galactic are developing vehicles to carry private citizens, researchers, and eventually tourists beyond Earth's atmosphere. What was once an elite privilege limited to a handful of astronauts may soon become an experience open to many. The sight of Earth as a glowing blue sphere against the blackness of space, a view that has forever changed those who have seen it. Private industry is also investing in space stations, mining ventures, and in-space manufacturing. Projects like Axiom Space's commercial station and Orbital Reef are building the foundation for an orbital economy that could one day rival industries on Earth.
As humanity extends its reach into space, the question of ethics and responsibility becomes increasingly urgent. Who owns the Moon, Mars, or the resources of an asteroid? How can we explore other worlds without contaminating them with earthly microbes or disrupting their natural environments? International treaties such as the Outer Space Treaty of 1967 set broad principles for peaceful exploration, but the realities of 21st century space activity are far more complex. The need for updated agreements governing property rights, environmental protection, and cooperation will grow as space becomes an integral part of human civilization. Artificial intelligence and biotechnology will likely shape the explorers of the future as much as rockets and spacesuits. Long-duration space missions expose humans to intense radiation, muscle loss, and psychological isolation. Scientists are developing new materials, medical treatments, and even genetic adaptations that could help humans survive and thrive beyond Earth. Virtual reality and neural interfaces may allow people on Earth to inhabit robotic avatars on distant worlds, exploring environments in real time without the risks of physical travel. Over time, the line between human and machine, Earth and space, may blur, giving rise to a new kind of interplanetary existence. But perhaps the greatest question is not technological, but philosophical. Why explore space? The answer lies in our nature. From the first humans who crossed oceans to the scientists who built telescopes to study distant galaxies, exploration is woven into the human spirit. It is the drive to know what lies beyond the horizon, to push the boundaries of understanding and existence itself. Space is the ultimate expression of that impulse. It is a mirror in which humanity sees both its fragility and its potential. The future of space exploration is not merely about rockets and planets, it is about perspective. Each new mission expands the window through which we view our place in the universe. As we reach for the stars, we are reminded that Earth, our small blue home, is precious and unique. The more we explore the cosmos, the more deeply we understand the interconnectedness of all things. One day, generations born on the Moon or Mars will look back toward Earth and see it as we now see the stars, distant, beautiful, and beloved. They will tell stories of the time when humanity first left its cradle, when our species chose not to remain bound to a single world. The journey we begin now is not just about reaching other planets. It is about ensuring the survival, evolution, and continuity of consciousness itself. In the end, the future of space exploration is the future of humanity, a promise written across the night sky, waiting for us to fulfill it.
The search for extraterrestrial life. Since the dawn of human thought, we have looked up at the night sky and wondered whether we are alone in the universe. Every culture across time has shared this same haunting curiosity. Are we the only sentient beings to gaze upon the stars? Or are there others, somewhere in the infinite darkness, doing the same? The search for extraterrestrial life is one of the most profound scientific and philosophical pursuits in human history, combining astronomy, biology, chemistry, and imagination in a quest to answer one of the oldest questions ever asked. Modern science approaches this mystery not through speculation, but through evidence, through the study of planets, chemistry, and the fundamental conditions that make life possible. The story begins with a simple observation. Life on Earth thrives wherever there is liquid water. From the deepest ocean trenches to volcanic vents and frozen glaciers, life finds a way. These extremophiles, organisms that survive in crushing pressure, extreme heat, radiation, and acid, have taught scientists that life is astonishingly resilient. If such creatures can survive in places once thought inhabitable, then perhaps similar forms of life could exist on other worlds under equally harsh conditions. This realization transformed the search for life into a scientific discipline known as astrobiology. Its goal is to understand the origins, evolution, and distribution of life in the universe. Instead of looking for green-skinned aliens, scientists search for biosignatures, the chemical fingerprints of life. These might include atmospheric gases like oxygen and methane, patterns of energy use, or even microscopic fossils preserved in rocks. Each discovery, no matter how small, brings us closer to understanding whether life is a universal phenomenon or a rare cosmic accident. Our own solar system is filled with promising candidates for life. Mars, once thought barren, now shows tantalizing evidence that it was once a warm and wet world. Ancient river valleys, dried lake beds, and minerals formed in water suggest that billions of years ago, Mars may have resembled early Earth. The Curiosity and Perseverance rovers have found organic molecules in Martian soil and rocks, while orbiters have detected methane plumes in the thin atmosphere, a gas that on Earth is largely produced by biological processes. Whether these signs point to living organisms or to geological activity remains uncertain, but the evidence keeps mounting that Mars once had all the ingredients for life. Farther from the Sun, the icy moons of the outer planets may hold even greater promise. Beneath the frozen crust of Jupiter's moon Europa lies a vast ocean of liquid water, kept warm by tidal heating from the planet's immense gravity. This hidden sea may contain twice as much water as all of Earth's oceans combined. Similarly, Saturn's moon Enceladus has geysers that shoot plumes of water vapor and organic compounds into space, suggesting a subsurface ocean rich in the chemical ingredients of life. NASA's future Europa Clipper mission and ESA's JUICE spacecraft aim to explore these alien oceans, seeking chemical traces or even microbial forms of life. Meanwhile, Titan, Saturn's largest moon, presents a different kind of chemistry, with methane lakes and a dense atmosphere that may resemble Earth's early environment. Though life as we know it would struggle in such conditions, Titan's exotic chemistry could point to an entirely different biochemistry, one based not on water, but on liquid hydrocarbons. Beyond our solar system, the discovery of exoplanets, worlds orbiting distant stars, has revolutionized the search for life. In the last 30 years, astronomers have identified more than 5,000 of these planets, many located in the so-called habitable zone, where temperatures allow liquid water to exist on the surface. Some of these exoplanets are Earth-sized and orbit stars similar to our Sun, while others circle small, cool red dwarfs that make up the majority of stars in the galaxy. The Kepler and TESS missions have revealed that planets are not rare exceptions, but common outcomes of star formation. Statistically speaking, there may be more planets than stars in the Milky Way, hundreds of billions of potential homes for life. New telescopes are now taking this search to the next level. The James Webb Space Telescope, with its powerful infrared sensors, is capable of analyzing the atmospheres of distant exoplanets, detecting gases like oxygen, carbon dioxide, water vapor, and methane, the same chemical markers that sustain life on Earth. Future instruments, such as the Habitable Worlds Observatory and large ground-based telescopes, will allow astronomers to directly image Earth-like worlds, searching for subtle signs of living ecosystems. It is entirely possible that within the coming decades, humanity may detect the first definitive evidence of life beyond our solar system, not through a radio message or spacecraft encounter, but through the quiet reading of starlight passing through an alien atmosphere. Yet the search for extraterrestrial life extends beyond biology. It also reaches into the realm of intelligence and technology. Since the mid-20th century, scientists have been listening to the cosmos through the Search for Extraterrestrial Intelligence, SETI. Vast arrays of radio telescopes scanning the skies for artificial signals that might reveal the presence of an advanced civilization. The first organized effort, led by astronomer Frank Drake in 1960, used a radio dish in West Virginia to listen for signals from nearby stars. Though no confirmed transmissions have been detected, the effort continues, expanding with new technologies, global networks, and even the use of artificial intelligence to sift through the immense data collected from deep space. SETI researchers often reference the Drake equation, a formula that estimates the number of intelligent civilizations in our galaxy based on factors like star formation rates, the number of habitable planets, the likelihood of life arising, and the longevity of technological societies. While the exact values remain uncertain, even conservative estimates suggest that the galaxy could host thousands, perhaps millions of civilizations at various stages of development. The silence we have encountered so far, known as the Fermi paradox, raises a profound question. If intelligent life is common, why have we not heard from anyone? There are many possible answers. Perhaps intelligent life tends to destroy itself before mastering interstellar communication. Perhaps alien civilizations use technologies we can't yet detect, or they simply have no reason to contact us. Some scientists speculate that advanced beings may choose to observe emerging civilizations from a distance, much as anthropologists study wildlife without interference. Others propose that intelligent life might be so rare that we are among the first, pioneers in a still young galaxy. Whatever the reason, the absence of contact does not mean absence of life. The universe is vast beyond comprehension, and even our most powerful instruments have explored only a tiny fraction of it. The discovery of extraterrestrial life in any form would be a turning point in human history. Even the detection of microbial life on Mars or a distant exoplanet would prove that biology is not